This strand of glass is thinner than a human hair, but it carries enough data to stream every movie ever made in under a second. Inside this factory, sand is melted, purified, drawn into glass threads, and bundled into cables that carry 95% of the world's internet traffic. Every email, every video call, every transaction. Every fiber began as a glass cylinder the size of a baseball bat, drawn into a strand thin enough to thread a needle, stretching over 200 kilometers. From beach sand to the backbone of modern civilization, this is how glass becomes the internet. This facility produces over 30 million kilometers of optical fiber per year, enough to wrap around the Earth 750 times. In 50 years, fiber optics replaced a century of copper. A single glass strand carries more data than every copper wire ever installed in New York City combined. Silicon tetrachloride reacts violently with moisture. A single container breach could halt production and require hazmat response. Over 1.3 million kilometers of submarine cable crisscross the ocean floors, carrying $10 trillion in financial transactions daily. The principle is visible at any scale. Light enters the glass and physically cannot escape, bouncing along the core at nearly 200,000 kilometers per second until it reaches the far end. The draw towers rise over 30 meters, providing the vertical distance needed to draw molten glass into fiber at 20 meters per second. The physics is elegantly simple. Light enters one end of the glass fiber and bounces along the inside, total internal reflection trapping the signal within the core across hundreds of kilometers. The journey begins with silicon dioxide, beach sand refined to 9/9 purity. A single impurity atom per billion degrades signal quality. The preform is the most valuable intermediate product, a solid glass rod worth thousands of dollars that yields hundreds of kilometers of finished fiber. Beach sand is roughly 95% silicon dioxide. Fiber optic glass requires 99.9999%. A purity level achieved only through chemical vapor synthesis. Chemical vapor deposition builds the fiber's optical structure layer by microscopic layer inside a rotating glass tube. Silicon tetrachloride and germanium tetrachloride gases flow through the rotating tube. The traversing burner at 1900 degrees causes them to react, depositing ultra-pure glass on the inner wall. Each pass deposits a layer just micrometers thick. 50 to 100 passes build up the core, the light-carrying heart of the future fiber. Precise germanium doping raises the core's refractive index above the cladding, creating the index difference that traps light inside the fiber. Every parameter is computer-controlled. The gas mixture ratio determines each layer's refractive index, a recipe refined through decades of optimization. The refractive index profile is the preform's DNA. Its shape, whether step index for long-distance telecommunications or graded index for data center applications, determines exactly how light behaves inside the future fiber. The burner temperature increases further, collapsing the hollow tube into a solid glass rod, the preform, with a doped core sealed at its exact center. The finished preform looks like a simple glass rod, but its invisible internal structure contains the precisely engineered waveguide that will carry data at light speed. Backlit, the preform reveals its layered architecture. The bright center is the germanium-doped core. The surrounding glass is pure silica cladding, together creating the waveguide that will carry trillions of data pulses. Every preform is profiled before drawing. The refractive index measurement must match the design specification within thousandths of a percent. Any deviation means the fiber won't meet transmission standards. The OVD method builds preforms from the outside in. Glass soot accumulating on a rotating mandrel in hundreds of passes, creating a porous cylinder later consolidated into solid glass. White opaque soot enters the furnace and emerges as clear transparent glass. Billions of particles fused into a single continuous solid. The transformation from chalky soot to crystal clear glass is among the most dramatic visual changes in the entire process. Chlorine drying removes every trace of water. A single water molecule per billion atoms creates a hydroxyl peak that degrades signal at critical wavelengths. 4 concentric layers: core, cladding, inner coating, outer coating, each measured in micrometers. The entire structure fits inside the period at the end of this sentence. Modern water-free fiber eliminates the hydroxyl absorption peak entirely, opening the full spectrum from 1260 to 1625 nanometers for data transmission and dramatically increasing usable bandwidth. Overcladding adds pure silica around the core preform, maximizing the fiber drawn from a single preform. The draw tower is the cathedral of fiber optic manufacturing, 30 meters tall, climate-controlled, and vibration isolated for atomic-level precision. The preform loads vertically into a graphite furnace at the tower's summit, heating the glass tip to over 2,000 degrees, softening it to warm taffy consistency. At 2,050 degrees, gravity pulls the molten tip downward, forming a thin neck that stretches into the beginning of the fiber strand. The fiber emerges at 125 micrometers, roughly a human hair's thickness, cooling from 2,000 degrees to room temperature in under a second. Helium cooling accelerates the temperature drop from 2,000 degrees to below 50 degrees within 2 meters of vertical travel. Without forced helium cooling, the tower would need to be 3 times taller. Laser micrometers measure diameter in real time, 125 micrometers with plus or minus 1 micrometer tolerance, a variation smaller than a bacterium. The light-carrying core is just 9 micrometers across, roughly 1/8 the diameter of a human hair. Every internet video, every phone call, every financial transaction passes through this microscopic glass channel. Bare glass is strong in tension, but fragile against scratches. The soft inner acrylate cushions against microbending that causes signal loss. UV lamps cure the coating in milliseconds at 20 meters per second. Any delamination between coating and glass creates a failure point. The harder outer acrylate provides abrasion resistance. Together, the dual layers increase diameter from 125 to 250 micrometers. The capstan wheel at the tower base controls draw speed with extreme precision. Draw rate directly determines fiber diameter. Faster drawing produces thinner fiber, slower produces thicker. The complete draw tower journey from molten glass to finished coated fiber takes less than 2 seconds. In that time, the glass is drawn, cooled, coated twice, cured twice, measured, and proof tested. Proof testing applies controlled tension to every meter in real time. Sections that fail break automatically and are spliced out, guaranteeing delivered fiber exceeds specification. A single preform yields over 200 kilometers of fiber, accumulated over hours of continuous drawing on precisely wound spools. Geometry verification ensures the core sits perfectly centered within the cladding. Even 1 micrometer of core offset increases splice loss, making concentricity as important as optical performance. A 1-meter preform becomes over 200,000 meters of fiber, a magnification of 200,000 to 1. ODR testing fires laser pulses through every kilometer of fiber, the reflected signal revealing attenuation and defects along the entire length. A ripcord embedded under the jacket allows field technicians to strip the outer covering by hand, eliminating the risk of cutting tools, slicing through buffer tubes, and severing fibers during installation. Premium single-mode fiber achieves below 0.2 decibels per kilometer, a signal traveling over 100 kilometers before needing amplification. 12 standard colors following TIA 598 allow technicians to identify individual fibers instantly during installation and maintenance. 12 colors, 12 fibers per bundle, 12 bundles per cable maximum. The color system enabling up to 144 individually identifiable fibers in a single cable. Water penetration testing submerges cable under pressure for 72 hours. The water-blocking gel and tape must prevent moisture from migrating to the fibers. Any ingress causes hydrogen-related attenuation that degrades performance over years. Buffer tubes are extruded around fiber groups at temperatures carefully controlled to avoid heat damage to the coatings. The gel filling prevents water from migrating along the tube if the outer cable jacket is breached. Ribbon fiber bonds 12 fibers into a flat strip that can be mass spliced simultaneously. All 12 connected in a single operation. Loose tube construction places fibers inside gel-filled plastic tubes, the glass floating freely, protected from crushing, bending, and thermal forces. Helical stranding distributes bending stress evenly. Without the spiral, outer fibers would stretch and break while inner fibers compress and kink. Aramid yarn, the same material in bulletproof vests, provides tensile reinforcement so installation crews can pull cables through conduits without stretching the glass inside. 7 layers of engineering protect 48 glass fibers thinner than hair. Every layer serves a specific mechanical or environmental function. Remove any one, and the cable fails in the field. High-density polyethylene jacket provides UV protection, moisture resistance, and durability for cables spending decades in weather and soil. The finished cable looks deceptively simple. Inside that black cylinder, dozens of glass fibers thinner than hair carry data at light speed through a structure built to survive decades underground. Before splicing, each fiber end must be cleaved to atomic-level flatness. The diamond blade creates a controlled fracture. If the end face angles more than half a degree from perpendicular, the splice loss becomes unacceptable. Finished cable winds onto reels holding 2 to 12 kilometers each. The largest reels weigh over a ton. Submarine cable is the most complex product. Steel armor, waterproof copper sheathing, and power conductors creating a cable that survives ocean pressure, anchors, and shark bites. Steel wire armor protects direct buried cables from rodent damage and accidental dig-ups. Rodents, particularly gophers and squirrels, cause a surprising percentage of fiber network outages by chewing through unarmored cables. Microcables as thin as 3 millimeters enable fiber installation through existing building conduits, eliminating the disruptive construction that once made fiber to the home prohibitively expensive. Indoor cables are slim and flexible. Outdoor cables resist weather and rodents. Submarine cables survive the crushing pressure of 5-kilometer depths. Submarine fiber optic cables are laid by specialized ships that unspool cable from massive tanks, feeding it over the stern into the ocean, along precisely plotted routes across continental shelves and abyssal plains. In cross-section, a fiber optic cable reveals its layered architecture, colored glass fibers within gel-filled tubes, surrounded by strength members and protective jackets, each layer serving a specific engineering function. Mechanical testing simulates a lifetime of stress, temperature cycling from -40 to 70 degrees, crush loads, bending, and water immersion. Tensile testing pulls the cable to maximum rated load while measuring optical attenuation simultaneously. The fibers must maintain full signal quality at peak stress. Temperature cycling simulates 25 years of seasonal stress in weeks. The fiber must maintain performance across the entire range without degradation. Fusion splicing joins fiber ends with losses below 0.02 decibels. An electric arc, melting both faces into a continuous strand. Bend radius testing determines how tightly the cable can be routed around corners during installation. Modern bend-insensitive fiber maintains signal quality at radii as small as 5 millimeters, enabling routing through tight building spaces. Under magnification, a perfect fusion splice is nearly invisible. The glass cores align to within a fraction of a micrometer. Misalignment of even half a micrometer causes measurable signal loss. 12 towers in continuous rotation. While 1 loads a fresh perform, 6 are actively drawing. 3 are in spool changeover, and 2 undergo scheduled maintenance, ensuring maximum uptime across the production floor. In the field, installation crews trench, bore, and pull fiber optic cables through underground conduits, connecting homes, businesses, cell towers, and data centers to the global network. Inside data centers, fiber optic cables connect thousands of servers in dense networks, carrying the cloud computing, streaming, and AI workloads that define modern digital infrastructure. Over 500 million kilometers of optical fiber are installed worldwide, with annual production exceeding 600 million kilometers and accelerating. Research and development pushes fiber performance further every year. Next-generation designs promise to multiply data capacity by orders of magnitude using the same physical infrastructure. Hollow core fiber replaces the glass core with air. Data moves closer to the true speed of light in vacuum. A 19-core fiber prototype has demonstrated over 10 petabits per second, the entire Internet's traffic through a single strand. In the field, every cable segment must be spliced to the next, often in underground vaults or on utility poles. A skilled splicer completes a fusion joint in under 3 minutes with losses below 0.05 decibels. The same basic glass fiber design has increased its carrying capacity nearly 1 million times since 1980 through improvements in lasers, amplifiers, and signal processing rather than changes to the glass itself. In hollow core fiber, light travels roughly 47% faster than in solid glass fiber, a difference measured in microseconds per kilometer that translates to billions of dollars in high-frequency financial trading. Multi-core fiber packs 7 or more independent waveguides into a single strand, one fiber replacing an entire bundle. Wavelength division multiplexing sends dozens of independent channels through one fiber, each carried by a different color of laser light, all sharing the same glass strand. 100 WDM channels at 400 gigabits, each yields 40 terabits, per second, enough to carry every phone call on Earth simultaneously. Back on the production floor, 12 draw towers run simultaneously, each one producing fiber at 20 meters per second, 24 hours a day, 7 days a week. Transmission records have doubled roughly every 2 years since fiber was invented. A single fiber today carries more data than the entire global internet did in the year 2000. Erbium-doped fiber amplifiers boost signals optically, no electrical conversion. Amplifiers spaced every 80 kilometers enable transoceanic cables spanning 15,000 kilometers. Draw tower operators monitor dozens of parameters simultaneously. A deviation in furnace temperature of just 5 degrees changes fiber diameter enough to move it out of specification. Preform changeovers happen every 8 to 12 hours as each preform is consumed. Minimizing changeover downtime is critical. Every minute of idle tower time represents kilometers of lost production. The cable assembly line runs at over 100 meters per minute. The stranding, taping, and jacketing stages synchronize to maintain constant cable quality throughout the production run. Every reel of finished cable is end-to-end tested before shipping. The test certificate accompanying each reel documents the measured attenuation of every individual fiber, the buyer's guarantee of optical performance. The test certificate is a legally binding quality guarantee. Any fiber that fails to meet the stated performance allows the customer to reject the entire reel, making pre-ship testing essential. The warehouse holds over 10,000 kilometers of finished cable at any given time. Inventory valued at millions of dollars, awaiting shipment to telecommunications companies and contractors worldwide. Each 12-hour shift produces over 1,000 kilometers of finished fiber per tower. The night shift inherits stable running conditions and the responsibility to maintain them until dawn. Connector polishing requires nanometer-level flatness. An invisible scratch causes reflection and signal loss at every connection point. Network operations centers monitor every fiber route in real time. A single cable cut from a construction excavator or a ship's anchor can disrupt millions of connections until a repair crew splices the break. Under interferometric analysis, the connector end face must meet sub-nanometer flatness standards. Every connector in the global network must achieve this precision. Billions of glass-to-glass junctions maintaining signal integrity. Domestic cable ships by truck directly to installation sites. A single flatbed carries enough fiber to connect 10,000 homes to the internet. International orders ship by ocean container. Cable reels cushioned against vibration that could stress the glass fibers during the multi-week ocean transit. Every 5G cell tower requires fiber optic backhaul, a direct cable connection to the core network. The global 5G rollout is driving unprecedented demand for fiber production capacity. Around the clock, around the calendar, the factory produces the glass threads that connect humanity. Every email, every video call, every emergency dispatch, carried by fiber made in facilities like this one. Global data traffic doubles roughly every 2 years. Fiber optic infrastructure must continuously expand to prevent the internet from becoming a bottleneck to economic and social progress. Glass waste from preform fabrication and fiber breaks is collected for recycling into specialty glass applications, maintaining material value even after production failures. A single optical fiber carries more data than a copper cable bundle, the diameter of a telephone pole. The infrastructure savings in material, weight, and installation cost are enormous. In data centers, fiber's small size and light weight are critical advantages. A single fiber cable replaces dozens of copper cables, freeing space, reducing cooling requirements, and lowering fire load. The world's largest data centers consume hundreds of kilometers of fiber internally. Google, Amazon, Microsoft, and Meta each deploy more fiber optic cable than most national telephone companies. The draw towers never sleep. Shutting down wastes the perform and takes hours to restabilize, making continuous 24, 7. Operation, the only economical approach. Production planning balances hundreds of customer orders against 12 draw towers and multiple cable lines, optimizing the sequence to minimize changeovers while meeting delivery commitments. From raw silica to finished cable, the manufacturing process spans roughly 72 hours. In that time, SAN becomes glass that carries the signals connecting 8 billion people. The 300 workers in this facility are building the infrastructure of the future. Every meter of fiber they produce carries the data that powers modern civilization, from streaming video to life-saving telemedicine. Daily quality reviews track every metric across all 12 draw towers. A trend showing gradually increasing attenuation on one tower might indicate furnace contamination. Caught early before it produces kilometers of off-spec fiber. Raw material purity testing catches contamination before it enters the process. A batch of silicon tetrachloride with 10 parts per billion of iron would produce fiber that fails attenuation specification across the entire preform. 30 million kilometers per year. 12 draw towers, 2,000 degrees. 125 micrometers. A strand of glass thinner than hair, carrying the weight of the modern world. That is how sand becomes glass, glass becomes fiber, and fiber becomes the invisible backbone that carries 95% of everything the internet delivers. From a grain of sand to a pulse of light traveling at 200,000 kilometers per second, through glass so pure that you could see through a 100-kilometer window. If this journey fascinated you, subscribe and hit the bell. Next time, we're heading inside a factory where cocoa beans become $100 chocolate bars.